Well, good morning and welcome to the CMBR-Conference on Blue Growth. I have the pleasure to chair this first session, and I'm researching in the Institute of Marine Biology, Biotechnology and Aquaculture, who hosts the event, and would like now to invite Dr. Magoulas, Director of HCMR and Coordinator of CMBR, to open the conference.
Hello, everybody. Welcome to our web conference. It is a common belief in our days that the great challenges of our days, that is the lack of resources and the increase in inequality of wealth, can be best addressed by supporting the development of blue growth and blue bioeconomy. Greece is a country with a tradition of thousand years of living by the sea, of traveling along the sea, and practicing commercial and other operations through the seas. At the same time, in our days, Greece is the top of the world of shipowning, being the first country in the globe in the number of boats in the commercial fleet. It is not surprising then that Greece, together with France, was the first country to sign the established the founding agreement of EMBRC, of the European Marine Biological Resource Centre. And since then, this collaboration, our incorporation into this important European research infrastructure, which is, to our opinion, but also to opinion of many other people, the best, the most important, the main research infrastructure in Europe for marine research and the development of blue growth. So our relationships have been very productive since then, and we are very happy about this. The project CMBR, Center for the Study of Marine Biological Resources, was actually a product of this collaboration. And this was clearly so because we have got a lot of help and support from the EMBRC Europe in order to create our research infrastructure. CMBR is an RI that promoted networking of the main research and academic organizations in Crete, working directly or indirectly with marine research. This was another very good contribution of CMBR, but included also important players outside Crete, and most precisely the University of Athens and the University of the Aegean. But we also included important players outside of the narrow framework of CMBR. For example, the Research Center Athena in Athens, as well as the Athens University of Economical and Business, of Economics and Business. And so we are very proud that we have contributed to the creation of a big, very strong, already strong, powerful community for marine research and blue growth in Greece. I'm very happy to see here that we have many prominent, this meeting brings together many prominent researchers from different, working in different aspects of blue growth. And we owe many thanks to all of you, and I'm confident that this meeting is going to be a good success. Thank you very much for your presence here.
And now I would like to invite Dr. Nicholas Spade, the CEO of EMBRC, with which, as Dr. Magoulas mentioned, we have a very strong interaction, and we have strong support by the headquarters, which is in Paris. Nicholas, please.
Good morning. Thank you very much for the introduction, and thanks for the opportunity to be here today. It's quite exciting, and I think the topic is really good. I think Antonis has already put his fingers on some of the really important points around blue growth. I think it's also always been an ambition for EMBRC to work very hard to try and improve this, and particularly concentrating on the regional aspects is always something we thought was really, really key. As a distributed research infrastructure, we have an advantage in being flexible in that we are positioned in what is usually peripheral maritime regions, but it also means that we have the ability to adapt. And it means that we can listen and we can change our setups, it can change our expertise depending on what is needed locally, both in terms of research, but also in terms of innovation. So I believe you have my presentation already. So would you like to run that, and then I can take any questions afterwards?
Hello, everybody. My name is Nicholas Pate. I'm the Executive Director for the European Marine Biological Resource Centre. I want to thank the organisers for the opportunity to participate in today's meeting and to share our view on the role of European research infrastructure in supporting blue growth. So, overview of what I'll be talking about today. So quickly, I want to just run through what a research infrastructure is. And then go on to just talk a bit about blue growth in the sense of what I'll be talking about, which aspects I'll be focusing on, and then look at why marine biological resources are important, and then using EMBRC as an example and demonstrating what a research infrastructure can do, and particularly what EMBRC does and the services that we offer. And then talk quite briefly about other research infrastructures as well, before then going on to talk about how research infrastructures fit in with blue growth and how they can act as drivers. So research infrastructures, what are they? So this is a term that's now been around for a good 10 years, and I think there's probably still quite a bit of confusion about what we mean when we speak about research infrastructures. So research infrastructures are defined by the European Commission as facilities that provide resources and services for research communities to conduct research and foster innovation. So essentially, these structures are set up to ensure that particular areas of research can be pushed forward, that we can invest together, avoiding duplication, and really create strong innovation communities around these topics. So generally, there are three different types of research infrastructures. You have the single site infrastructures. So these are things like your synchrotrons, which are based around a single central facility that people come and use. Then you have distributed research infrastructures. So these are the ones that, as the name suggests, are split over multiple sites in multiple countries. And then you have the virtual ones, which are the ones that are based around data and modeling and so on, which doesn't necessarily have a physical presence for the users to access, but are usually accessed either through data or web portals. So there are 5 main groups of research infrastructures in Europe. So they are energy, environment, health and food, physical sciences and engineering, social and cultural innovation, and digital as well. And just to give you an idea of just how many infrastructures there are, you can see the list of all the ones that are currently on the research infrastructure roadmap. So EMBRC fits into the group of health and food, which essentially are the life sciences, but being marine stations predominantly, we work very much as well in the domain of the environment. So we really straddle these two communities and serve these two communities all the time. So in terms of blue growth, so there are generally the main topics around blue growth and the main sectors are shipping, transport, fisheries, and offshore oil and gas. So these are, you could argue, are the backbone of the blue economy. However, for today's presentation, I would rather focus on the 5 growth sectors. So they are the ones that are listed here below. So they are biotechnology, renewable energy, culture, coastal and marine tourism, and mineral resources. What I really want to talk about is sustainable blue bioeconomy and blue growth, because I think this, I'm a very big fan of this diagram. I think it illustrates very well how we should be moving forward in blue growth. So here in the center, we have our growth sectors. These are our technology. This is our innovation that we want to drive. And these then lead on to providing jobs, creating income, and generally creating a prosperous society. However, in order for this to work, and particularly anything that is based on bioeconomy and the environment and natural resources, I think it's extremely important that we also bear in mind the element of sustainable. We cannot have an economy that's based on a finite resource that we are not also managing in an intelligent way. And let's not forget that sustainability offers also opportunities to innovate in the blue economy. So for the duration of this presentation, this is really the format I'll be looking at, focusing on the biological aspects, so really biotechnology and aquaculture, and the sustainability bit. So why build a research infrastructure for marine biological research? So I think it's very obvious that blue growth and the blue economy is extremely important in Europe. We are, in many aspects, a maritime continent. We have strong traditions with the sea. We have very strong maritime sectors. So it's clearly important to Europe. But if we take a step back, we can also see that the oceans are omnipresent, and they are important to explore for many reasons. Chiefly among them is, first of all, 75% of life and about 99% of living space on the planet is the oceans. We source today about 16% of the animal protein that we consume worldwide from the oceans, and about half of the oxygen we breathe is produced by plankton and other marine organisms. At the same time, in terms of biodiversity, it's incredibly rich. Of the 34 fundamental animal lineages that we have identified in the Tree of Life, 32 of them are present in the sea. And this huge biodiversity offers significant potential for new biodiscoveries for human benefits in the sectors of food, energy, innovation, but also in health and medicine. But at the same time, we have to bear in mind that the oceans and seas and its biodiversity are still actually very poorly understood, especially in terms of harvesting, and especially outside the traditional areas of harvesting like fisheries. So what happens if we start harvesting vast amounts of algae, for example? So we really have to remember that a strong blue economy is based on innovation as well as sustainability, to ensure that the resources that we rely on, we can continue to exploit and use in a sustainable manner. So what is EMBRC? So the European Marine Biological Resource Centre is a distributed research infrastructure. We're found at the moment in 9 countries, and we have 45 sites for research and experimentation, going all the way from northern Norway all the way down to the tropical coral reefs that we get in the Red Sea in Israel. Our mission is to provide access to marine biological organisms and their habitats for experimental purposes and applied research, promote sustainable use of marine resources, deepen fundamental knowledge on marine organisms and their role in the environment, and really make sure that we're there to push the frontiers of science, explore marine biodiversity for new products, inspiration and innovation, and finally promote the use of marine experimental models in mainstream science. Now, within this mission of trying to push forward the frontiers of science, we therefore then also work on developing a number of tools and techniques. So the ones that we're currently working on at the moment is cryopreservation. This has in the first instance been very much around how we preserve our microorganisms in our culture collections, but we're now then also moving towards how we preserve gametes in a viable fashion in aquaculture, for example. We work a lot on husbandry, on our model organisms, but also closing life cycles of micro and macroorganisms. We work on developing genomics tools so we can genetically manipulate these organisms. We work on new experimental systems. One of the ones we're working at on the moment are on-land tidal systems where we can simulate various things. We are working to establish a genomics observatory so we can start monitoring biodiversity. And finally, we're building a pipeline for bioprospecting so we can support this activity really all the way from the organism up to the characterization and screening and scale up. So in terms of services, we offer, these are probably the 2 main areas of access that we provide. So first of all, ecosystem access. So this allows people to go into the sea, do their sampling, again, put in place in situ experiments. We offer access to a very broad selection of environments, from kelp forest, coral reefs, lagoons, all the way to relatively deep environments. And here we find our small research vessels, our sampling facilities and equipment, our scientific diving teams, and a small number of submersibles and ROVs for doing surveys. The other big activity is, of course, providing access to biological resources. So this can both be either on-site, or we can also ship them to users' own institutes. And so these come from biobanks. We have a large number of specialized culture collections, including bacteria, phytoplankton, fungi. We do rearing of aquaculture or animals. We can organize collection in the wild of wild types of most of the organisms that are present by the shore. And we also offer some taxonomic services to help identification of various groups. We also offer then on-site access to experimental facilities, meaning that researchers can come on-site to carry out their experiments close to the sea and to the source of the organisms. So here we have our aquaria and tanks and microcosms. So these are general set up in a combination of different size tanks. And these are extremely modular systems that really can be set up to accommodate pretty much any experiment that a scientist or a company wishes to carry out. We have climate control rooms, so we can look at environmental effects. We offer wet laboratories and dry laboratories. To complement this, we then have our technology platforms. So these allow a first step of analysis for researchers before they take their results home to continue their work. So this includes bioassays, bioimaging, molecular biology and omics tools, remote sensing and telemetry, and structural and chemical analyses. And then we have what we term our support services. We have a number of long-term ecological time series available through EMBR. Number of software for data analysis. We're, for example, working on creating a genome annotation tool that can be used by a community, so it can be annotated and assembled together. We then have also our library services. So these are historical texts, they are bibliography databases, and so on. Some of these texts are extremely rare and offer a very good insight to the historical biodiversity and state of the areas where we are present. We then also have marine training, which is our arm dealing with the training aspect. So this is, first of all, a worldwide catalog of marine training courses that can be accessed online, but it's also a platform for hosting online courses, and it offers a number of tools as well for online teaching. Then we have as well training facilities, conference rooms, training laboratories, and on-site accommodation as well in some of our sites, which means that people can come on site, they can stay there if they need to be there for a long time. So this is quite popular. In terms of ocean health and sustainability, so I've mentioned this already earlier, that a successful blue economy relies on a healthy ocean. And to do this, we need effective tools to monitor the health of biodiversity. So EMBRC is now trying to launch in June the European Marine Omics Biodiversity Observation Network. So this is a coordinated and we think first of its kind genomics observatory based across 15 EMBRC sites, where we will be following the same protocols and the same data collection with very vigorous metadata standards and protocols. We'll be collecting data on water column, on soft sediments and hard substrates. There will be a focus on microorganisms, but for the soft sediments and the hard substrates, we will also be looking at the mesofauna. The idea here is that we can, from Europe, start to contribute genomics data to a global observatory network, and really start feeding data into essential ocean variables and essential biological variables. The data will also form a minimum background data to support microbiome research as well, as really a minimum to make that a reality is to understand what we have within our community. And as I'll show a bit later on as well, is that this genomics observatory will also provide opportunities for industrial links and regional management. Bioprospecting is the other big service that we're working on at the moment. So here we're aiming to be able to support discovery of novel compounds and bioactive substances from marine biodiversity, focusing on the groups of organisms that we have particular strengths in across EMBRC. So this builds on our expertise in culturing and working with diverse organisms. Of course, the platforms that are involved with doing bioprospecting can be found in many places. But what we have in EMBRC and the expertise that we provide is around the organisms that we can manipulate very well, that we can culture very well. So we will offer screening environments for consortia and isolation of organisms. We'll be offering chemical characterization of compounds, and essentially we'll be assembling a full pipeline for bioprospecting in EMBRC to provide a one-stop shop for bioprospecting support, meaning that we can go all the way from organism to scaling up, or a company or researchers can come anywhere along that pipeline and pick the services that they need or the capabilities that they might be missing to make it a reality. So, of course, offering access to biodiversity also means that we have a responsibility to provide biological resources in accordance with rules and regulations. So I would imagine most of you are familiar with access and benefit sharing, to many also termed the Nagoya Protocol. So we're working very hard to ensure that as the EMBRC, we can provide reliable and transparent access to marine biological resources. This means that we try to be a reliable and trusted partner. So that countries can deposit their marine biological resources with us, ensuring that we will not abuse these resources and ensure that they're used in accordance with the rules of the country. It also means that we can provide users with peace of mind when accessing biological resources, in that we offer them a safe environment to obtain resources with the knowledge that coming to EMBRC means that they have exercised what we call due diligence, meaning they have taken the necessary steps to obtain and use the resources within the rules set by the country of origin. So with that, we very much aim to facilitate access to marine biodiversity and try and help our research and innovation communities with a topic that is very tricky and for many people still a significant worry. So what are the benefits for researchers and companies to work with EMBRC and indeed other research infrastructures? Well, first of all, we offer a single access point to a large number of services, facilities, and expertise. This means that it becomes much easier for people to find what they need. In a sense, it also democratizes science, in the sense that it means anyone can get access to these facilities and organisms. In the past and historically, people would need to have a collaboration or know somebody somewhere that they could work with together. Here, really, there is no prerequisite or there's nothing that stops you coming to work with us, because we are open and will work with everybody. So it saves time and resources as well, even though the services in the EMBRC are costed at the point of use, meaning that they're not free to use. They are heavily subsidized for researchers, meaning that they provide a very, very good cost benefit, because it means we can give access to equipment and the expertise and technicians associated with them without having to make large investments in infrastructure and equipment. It means that people can work with veteran technicians that really know the platforms inside out and can very often also provide excellent advice on how experimental designs can be improved. From a company point of view, it means that they can access things, especially smaller companies can access equipment and expertise that they wouldn't necessarily have in-house. And I think particularly for companies, what's important is that using a research infrastructure and the services that we provide, we have a policy of user keeps intellectual property. So we lay no claim to any of the data or any of the intellectual property during our platforms. Of course, if we are involved as a partner in the project, meaning we have a development in the project, or we are giving our intellectual property, of course, then we are a partner in that and we share the intellectual property. So example of the some of the different types of projects we've given access to. So we had one that looked at skeletal growth mechanisms in elasmobranch fish. This is particularly interesting around cartilage and for biomedical applications. We had a very successful project with a company in the Netherlands that were looking at generating new and novel colors, also in an environmental friendly way by looking at bacteria. So that was a very big success. We have been working with aquaculture companies to do feeding trials for them. We've had people come in and screen our culture collections for various compounds, and we had one, for example, looking at novel treatments in malaria. And we had another one looking at green omers and the impact of climate change, because in some areas of Europe this is an important aquaculture organism, and they were trying to predict what climate change, ocean acidification, and temperature increase, what effects this would have on omers, productivity, and yield. Now, as I mentioned earlier on, research infrastructures are numerous in Europe, and there's a very rich ecosystem of infrastructures dealing with a very topics. In EMBRC, we're lucky because in the sense that we work both with the life sciences and with the environmental sciences, so we have a lot of potential collaborations. And really what they allow us to do is boost our own capabilities. So for example, we have a lot of demand for microscopy in EMBRC, and by working together with Eurobioimaging, this gives us much stronger capabilities in microscopy. We work together with LifeWatch, which give complementarity to our data, so they're working on new data workflows. Also, in terms of complementarity, we work with EU OpenScreen, so they provide even larger screening libraries for new compounds. We work with Elixir, which is the large research infrastructure for biological and life science data. So again, here in database linking and data mining. And finally, on the environmental front, in terms of observation, to both add context and complementarity in observation, we work with ENSO, we work with EuroArgo, we work with Jericho, and also now, since recently, with ICOS Marine. So, after giving you an overview of EMBRC, how can research infrastructures then be drivers and enablers of blue growth? So, research infrastructures tend to be found in distributed locations, especially those research infrastructures that are distributed. It's kind of in the name that they're found all over Europe. For EMBRC, most of our sites are found in peripheral maritime regions, and this is also where blue economy is typically important. So we've got fisheries there, which have been declining in many cases, and we often see that this is the places that, for example, new biotechnology companies pop up. Being distributed means that a research infrastructure can take advantage of this flexibility and can adapt to local needs. It means it's present in the territory, so it's in proximity to the local companies, so it can establish strong ties locally with them. So there, the research infrastructures can be used as a platform for collaborative research, where the researchers can work with companies who want to come in and benefit either from the platform or from the expertise in-house. And this means also that then this opens opportunities for the infrastructures to create novel services tailored to local needs. And this can be around aquaculture, it can be around the environment, it can be, for example, monitoring the planktons, looking for harmful algae, or monitoring invasive species, because this has impact on aquaculture and also on ports, for example. It means they can create workshops and training. These can be tailored to the local companies, providing specialist technique training or giving them training on new platforms, technologies. And then, of course, because of this rich environment of research infrastructures, it means they can also then link to the expertise both within the infrastructures in other regions, but also to the other research infrastructures and their expertise. So, essentially, what research infrastructures can provide is an insertion and a support to the local. So if we take this diagram, so the research infrastructure using EMBRC here as an example, essentially provides access to the bioresources and specialist platforms to support the local industry. Now, if that's then tied together with incubators and startups, to help support spin-offs, it means that they have that critical expertise and access to infrastructure early on, which means that they have smaller fees, and it's in proximity, so they can use it without having to travel afar. Adding to that, science parks, which then brings lots of companies together within a certain sector. It means that it gives space for industrial collaboration, and it means that there's business support allowing these spin-offs and startups to grow. Now, if then it's also then combined with a savvy regional government that then stimulates this environment by injecting money either to the incubators, to enabling the science parks, but can also inject money for example, personnel dedicated to support the local companies in the infrastructures. It sort of helps close the cycle and can really stimulate a strong industry sector within the government, as well as providing a link to the outside, to other regions with similar interests. An example in Crete is the UPBC, or the Underwater Biotechnology Park in Crete, which is part of EMBRC Greece. So the objective here essentially is to look at combining protection, conservation, and exploitation with observation, as well as looking at novel aquaculture. So you're combining nature-based solutions with experimental aquaculture and seafloor observatory and sensor deployment arrays, which means that companies can come in and take advantage of this rich environment to test new sensors, try new techniques, work with the local scientists for novel solutions. And I think this is a really nice example of this put into place and put into practice. So how do they then drive the regional growth? So the research infrastructures can be tuned towards regional strengths and smart specialization priorities. And here it's important also that the research infrastructures look at these S3s strategies where they are based to say, okay, what is needed and how does my research and my platforms fit in with what the local biotechnology and aquaculture sector needs. It then also offers a link between regions with shared S3s, allowing for strengthening competencies, joint investment, and increased collaborations, meaning that, for example, certain sectors that are important, let's say in Crete, can be connected with similar regions of interest in Italy or in Portugal or in Spain. And amongst those countries or regions, joint investment can be made, for example, in one facility that will support all 4 regions and with the same sectors of interest. And so by investing in these research infrastructures, essentially what they can do is provide a boost to competitiveness in the region because of this proximity of expertise and technology with the local companies. But there's also, as I said, this opportunity to found in sustainability and environmental monitoring, because it's not just about patents and new products when we get to the blue economy. So what opportunities there in the environment? So because blue economy depends on healthy environment. So first of all, we have observation of the ocean, both physical and biological, because if we have an industry that is strongly dependent on the sea, our ability to understand and predict the conditions for the local industry will allow them to make safe investments. It'll allow them to ensure that what they're doing, that they're in the right place and choose the right products for where they're based. But environmental monitoring also opens up new avenues of support for services for industry. So, for example, these can be water quality checks for a fish farm. It can be looking at invasive species in the local port, or it can be for detection of harmful algal blooms, which allows an aquaculture producer to remove his organisms before that they are destroyed by an incoming algal bloom. So all of these things are, of course, novel and innovative as well, and again allows this blue economy to thrive and be strengthened by this additional support. So in summary, I hope I've managed to demonstrate that, first of all, research infrastructures offer a diverse set of platforms, skills, and competencies to enable innovation. There's lots of research, and a lot of these infrastructures are already at the cutting edge of research, which is then something that can be made available locally. The distributed research infrastructures have this additional advantage of being situated in a region and therefore can adapt and specialize according to local and regional needs. And this then creates a space for industry and researchers to collaborate. And this, I think, is also very important because it brings in expertise that can drive novel products and can improve products for this industry as well, especially when they have problems that need solving. So they can boost local research and innovation capability but they also need to be provided with the right environment. You can't just have a research infrastructure and then expect everything to happen magically. It does need to be connected with a strong industry base. It does need to be able to support the startups and with the business parks. And this really is something where you then need a strong regional policy and a strong regional government with an interest in driving innovation forward to say, okay, we know these are the puzzles. We will give them the tools and maybe also a bit of financing necessary to kickstart things by adding some extra human resources or by giving financial vouchers to start up to use research infrastructures for free, for example. And finally, that it can be an important link in enabling blue economy and ensuring sustainability, and also within this sustainability aspect that we also look to innovate and create something new. I thank you very, very much for this opportunity, and I'm more than happy to take any questions that you may have. Thank you very much.
Nicholas, thank you very much for having presented the comprehensively in BRC. Being from the inside, I know how much effort this requires to make progress. I will take the two questions that we have in the chat with the comment that S3 RIs are a new paradigm in research organization, and this is unique to Europe as far as I know. So do you see, what are the challenges you see for further development in the RIs? And also, I add to this question of Dr. Magoulas, you presented interaction with other RIs, and there are families of it. There are interfaces. Is it always easy to collaborate on these interfaces? Is there a trend for competition or more for collaboration on that?
Thank you, Georgios, for all the questions. So in terms, first of all, of restricting the development, I think the infrastructures were plagued from the beginning by terrible jargon, and that people were struggling to understand what they were. I think that has improved a bit, but I think we're still really lacking a strong encouragement to use the infrastructures. So what I think would be really nice to see is more intent from national governments and also regional governments to try and utilize these tools that have been invested in and sort of put them at the heart of the research landscapes that they have. Normally, investment in a research infrastructure indicates that that sector is incredibly important. So an investment in EMBRC would normally signal that the country and or the region considers that marine biological resources are incredibly important. And what we offer is essentially trying to drive that community forward by creating the platforms and developing the tools that are needed. So a stronger drive to use us and encouragement to use us, I think, is what's really lacking behind in getting it to work. I think part of the challenge sits in as well is that, you know, on one hand, it's good that we are in the peripheral maritime regions where we're close to the industry. But in many cases, this puts us also in places where tourism is the predominantly important industry. It'll be interesting to see over the next 5 or 10 years now with COVID, whether we will see a trend of diversification even in the strong tourist sectors. And this might even be a time to start considering that you know, there are many resources and there are many other things that can be done. And I think particularly on the industry side, it would be nice to see, you know, we've got a couple of regions in the MBRC where we're seeing the regions being very heavily involved, where they're encouraging companies to use the infrastructure. They're even in some places paying for staff that are, you know, dedicated to servicing industry. And this seems to be working very well. But it does mean, it does take a decision or a realization that, you know, this is a tool to be invested in to try and drive the industry forward. In terms of collaborating with other infrastructures, because we all kind of face the same challenge, I'm very happy to say that we have a very strong collaborative community, I would say. We work very hard together because we all face the same challenges, and predominantly we are complementary rather than competing. So even amongst Horizons calls and so on, we do have a tendency, okay, say, well, this is more your niche, you should lead that. Where can we be complementary? Or we contact each other to bring in expertise where it's relevant. But again, around the challenges of research infrastructures, we're not getting involved in as many Horizons projects as we would hope. And I think it is also a case that many people don't realize that an infrastructure doesn't have to be, a big, expensive beneficiary in a project. There can very happily be an outsider that are providing services or support, depending on what the needs are. So I think what would just be nice is more people getting in touch, and so they can see what it is that we're doing. But I think we also have a job to do to start innovating a bit more in what we're doing around our services and what we're going to offer. And I think some of the things that I was presenting today is also some of the things that we are thinking about in the MBRC for the future. Then there was the last part of the question, which was about the challenges of establishing MBRC. I would say that was a lot of this was really, I think, first of all, we all needed to understand what it was that we were doing. We were in the early projects to be established as research infrastructures. And I think for many of us, it took us probably 5 years to understand what it was we were trying to build, and then getting all the support behind it and getting it established. And as you mentioned yourself, Georgios, trying to get everybody working together and established and creating and building national infrastructures in all the participating countries. It's been hugely challenging, but I also think it is starting to pay off. I think we're starting to see things operate much more smoothly, and we are. I mean, it's nice to see we are getting more users in, and we are generally seeing people being really happy with what they're getting. And I think it's also that realization of people finding out that we do have something really interesting to offer, and on a horrible, cold, and economic plane, it makes a lot of financial sense to use the MBRC as well. It's much cheaper to use us than it is to buy the equipment yourself and operate it yourself. And we give huge flexibility. You can run an entire research project through our combined facilities.
Thank you. Thank you very much, Nicholas. I discovered myself working with you and with other countries that this takes a lot of creativity and effort of each one. And I don't know if it's your feeling also, this was a very democratic process to build it. Everybody put his part and his ideas, and they're always been taken into account. And I think especially at this period, this is really very, very effective and very real. Do this kind of democratic process, you think, happens at a higher level? Do you interact with Brussels yourself, any tool that MBRC or other RIs that you have? Are there instruments in Europe that support this kind of bottom-up and top-down approaches to meet in the middle?
I think in EMBRC we always had a strong community working together, so there was not a strong need for a heavy top-down machine. And I think one of our strengths has always been that we've developed things according to what was important to everybody and been inclusive. So we've been very bottom up and only top down when it was needed. I wouldn't say that this is a universal functioning in the MBRC. This is the way that we operate, and I think very often the MBRC doesn't necessarily operate like everybody else does. We have our way of doing things, and I think it works quite well. So we've never been scared about doing things our way and doing it our own way. In terms of working with other institutions. So we've been building various fora within the research infrastructures thematically. So right at the beginning of my talk, I talked about the life science research infrastructures and the ENVI community. So these are the life science infrastructures and the environmental infrastructures, and we meet a couple of times a year amongst the directors to discuss strategy and important points for us. We then have also created the ERIC Forum, where we discuss things that are pertinent to the established research infrastructures. There's a lot of exchange on best practices there. And all of these fora are very bottom up. They're very much everybody bringing to the table what's necessary. And we use this mechanism then to go on to Brussels, either as our thematic communities of life science or environment, or as the entire research infrastructure community, depending on the message and depending on the topic. And so, for example, with the cancer missions, the missions in general, so obviously cancer being one of the ones that we're also interested in supporting. we've been using the mechanism very much to write letters of intent to make it clear to the commission, to the mission boards and so on, how the research infrastructures can contribute. And that's now also manifesting itself within the InfraServe calls that are coming out, which are several sort of dedicated towards many of these missions and themes. And I would say in the past as well, I think we've been listened to quite a lot as well within the research infrastructure unit in Brussels. We've had the unfortunate situation in the past year or so in that we've changed heads of unit a few times in a short amount of short space of time. And this has made communication very, very complicated. And so we're really waiting for the new one, the new chair to really come in and take up the post so we can start speaking again. But really, I mean, COVID has made this hugely difficult, whereas before there was always somebody from the research infrastructure community going to Brussels and speaking to people at the Commission. That's not been possible at all. And there's no doubt that this has really hampered our work and our visibility with the Commission at a potentially crucial time of the start and kickoff of Horizon Europe.
Okay, Nicholas, thank you very much for staying with us to follow the presentation of CMBR this morning sessions. And thank you for being supportive to our national efforts.
No, thank you, Georgios. It's always a pleasure, and it's always lovely working with you guys. You've got so many exciting things going on. So I'm looking forward to see the rest of the talks this morning.
Thanks. Thanks. So now I would like to invite my colleague, Dr. Nikos Papandroulakis, who is a researcher in the Institute of Marine Biology, Biotechnology and Aquaculture, and expert in aquaculture, biology and engineering.
Hello again, ladies and gentlemen. I'm going to talk to you about the Center for the Study and Sustainable Exploitation of Marine Biological Resources, or CMBR. What is CMBR? It is a project, but at the same time it is a research infrastructure, an RI, which is coordinated by the Hellenic Centre for Marine Research, or HCMR, and more specifically by its Institute of Marine Biology, Biotechnology and Aquaculture, or IMBBC. At the same time, CMBR is the project in the context of which the present web conference is organized. CMBR is EMBRC based. This means that it was developed on the lines that were formed because of the participation of our institute IMBBC in EMBRC ERIC. Dr. Nicholas Pate, in his keynote speech just before, gave you already a clear picture of what EMBRC ERIC is. So I do not need to describe again here this important European research infrastructure. It should be noted that CMBR covers also the activities of another important European research infrastructure, LiveWatch, and so it is closely linked to it. In any case, one can say that CMBR corresponds actually to the construction phase of EMBRC GR, that is, of the Greek node of EMBRC. CMBR is included in the Greek roadmap for research infrastructures. It includes a wide variety of fields topics, some of which you can see here: multi-omics bioprospecting, designing of a multi-use offshore platform, development of an underwater biotechnological park, advancing mesocosm facilities, supporting genomic observatories network, and improving experimental and computing facilities. In addition, CMBR interacts also with the other research infrastructures running at IMBBC, that is LiveWatch already mentioned, Elixir, and Eurobioimaging. CMBR is a 3-year project starting from the year 2018, which means that the current year is the last year of its duration. It has been funded by national sources with an amount of 4 million euros, of which 2.6 million euros were devoted to HCMR. In general, CMBR aims to reach the level of an internationally competitive research infrastructure for the sustainable and effective exploitation of marine biological resources. Two of its most important characteristics are: firstly, that it has the ambition to be the main national vehicle for blue growth, and secondly, to support the notion of smart specialization in Greece, but also in the area of the Eastern Mediterranean. Now I will give you a short historical review of the developments that led to the funding of CMBR. In December of 2014, the Greek National Roadmap for Research Infrastructures was released. 25 infrastructures were included in it, and CMBR was one of them. 2 years later, in the year 2016, there was a re-evaluation of the 25 RIs in the roadmap, and 20 of them were finally qualified. It should be noted that CMBR was one of the three only infrastructures that met all 9 eligibility criteria of the National Strategic Reference Framework, or ESPA in Greek. In the same year, 2016, a national call for proposals for supporting research infrastructures was released. We submitted our proposal for CMBR in the October of the same year. The results of the evaluation were released next year, and as already mentioned, CMBR won a grant of 4 million euros, and the official starting date of the project was the February of 2018, and its duration was 3 years. There are 9 partners in CMBR belonging in 7 different institutions. HCMR, with IMBBC in collaboration with the Institute of Oceanography, have the coordinating role. Other partners include the University of Crete in Heraklion, with the Biology Department and the Medical School, the Technical University of Crete in Kania, with the Department of Electronic and Computing Engineering, the Foundation of Research and Technology Hellas in Heraklion, with the Institute of Computer Science and the Institute of Molecular Biology and Biotechnology, the Hellenic Mediterranean University in Heraklion, with the Department of Electrical Engineering. All these partners are based in Crete, but we have also 2 other partners outside Crete, the University of Athens with the School of Pharmacy, and the University of the Aegean with the Department of Marine Science in Lesbos Island. In the next slides, I am going to give you some information on the objectives of the project as they were formulated in its beginning. My colleagues in the talks that will follow immediately after my presentation will give you information on the advancement of these objectives and on the achievements of the project. I will present the 4 main actions of the physical content of the project, starting from the biotechnological applications. So between the objectives in this direction were the recognition and isolation of bioactive substances such as pharmaceuticals, cosmetics, enzymes, and so on, from marine microorganisms, especially from those living in extreme environments. The omic approaches, that is genomics, metabolomics, proteomics, bioreactors, bioassays for the detection of antibacterial, anti-inflammatory, and anti-cancer properties, the study of the complexity of marine ecosystems, linking genomic and biological diversity with the environmental parameters and changes. Finally, the networking with international initiatives such as the Genomic Standard Consortium and the Genomic Observatories. In our days, we all know very well that sea is the home to a vast, largely unexplored biodiversity, which actually constitutes a rich source of medicines and natural products. You can see here some examples of extraction of biofuels from the sea, of anti-cancer agents, and of drugs against malaria from algae, bryozoa, and the sponge. Talking about the directions in which biotechnological applications can be applied, we refer here to the molecular or genetic characterization of food, to the recorded characterization of genetic diversity in Greece, talking especially about breeds and varieties, to the investigation of microbial wealth in the seas, especially in the extreme environments, to the authentication and identification of geographical origin and the fight against commercial fraud, and lastly, the traceability and hazard identification in the food chain. Talking especially about applications in aquaculture, the project aims also in the development of genomic tools such as genomic libraries, back libraries, linkage maps, etc., to the genetic improvement in both traditional and new aquaculture species, and last but not least, to fighting disease in aquaculture. We move now to the second main action of CMBR, which is mesocosms. The mesocosm facilities of HCMR are a very important infrastructure, and this is true on an international scale, as they are adjacent to an extremely oligotrophic marine environment, which is that of the Eastern Mediterranean, and are complemented by a range of laboratories of the 3 research institutes of HCMR. The main objective of CMBR concerning mesocosms is to conduct large-scale experiments in relation to different topics, such as the global environmental problems, operating issues of disturbed marine ecosystems, nutritional relationships that support food webs that provide marine biological resources, and so on. The third main action of CMBR is the underwater biotechnological park. It has been established in a coastal area of approximately 25,000 square meters at a depth of 18 to 20 meters. The main goal of this park is the development of multi-parametric platform and of a scalable observatory at the bottom, which will allow continuous and long-term research of the local ecosystem. This can also support a wide range of experimental and demonstration activities, with special emphasis on the technology of technical reefs, the developments of innovative breeding technology for new species, and the creation of recreational diving parks. And now I come to the fourth part of actions in the CMBR project. It is well known that the coastal zone is subject to intense and constant competition for space and resources. One possible solution would be to go to the open seas, but this is a rather expensive exercise, and the solution would be to go for multi-use platforms, which mean platforms in which different activities coexist to reduce costs. Such activities could be aquaculture, but also renewable energy devices. There are already several EU initiatives for multi-purpose offshore platforms, such as the projects Mermaid, Tropos, etc. I will close my presentation with two slides which refer to two actions that were not officially part of CMBR, but they were developed in parallel and in linkage to CMBR. The first is the initiative of genomic observatories, which was organized in the context of the project assembled as a JRA and was coordinated by Dr. Giorgos Kotoulas. They include samples from 18 stations, out of which 15 are along Europe and 3 are from the Red Sea, the Antarctic and the Arctic Ocean. They include metagenomics, metatranscriptomics, metabarcoding and DNA analysis, and they refer to whole ecosystems such as they include the water column, but also the benthic communities. There are a lot of challenges related with it, but there are also a lot of promises and expectations of this initiative. The second action is the Ocean Sampling Day, which is a long-term monitoring of the oceans using metagenomics approaches. It includes approximately 200 stations. It is executed during the summer solstice. It started in the year 2014 and 2015 in the context of the project MicroB3, coordinated by Frank Oliver Gluckner, but then there was a period in which this was not executed, and OSD was relaunched during the year 2018, again in the context of assemblage, and again with Giorgos Kotoulas having played a crucial role for this. Concluding, I would like to mention that CMBR, by upgrading, completing and integrating existing facilities and infrastructures, provides stable access to two different types of ecosystems, to offshore ecosystems, thus allowing for the first time the use of a typically inaccessible environment, and the coastal ecosystem already in use for research and development purposes. It also offers opportunities for innovative biotechnological applications which can radically change the landscape in terms of sustainable exploitation of the marine biological wealth. Thank you very much for your attention and a lot of wishes for a successful meeting. Thank you.
Thank you very much, Antonis. I apologize for erroneously being hurried to introduce Nikos Papandroulakis. Antonis, I have a question for you. CMBR has a life of only 3 or close to 4 years now, while in BRC, it's in, say, not in the adulthood, but in its youth. So I think 4 years, it's not enough to build and implement it strongly in infrastructure, and this would need further support. This would correspond actually to the preparatory phase, the funding of CMBR. What do you think are the possibilities? What is the understanding of the government about the need of infrastructures, and if we have tools and instruments to pass the message?
First of all, I would like to say that actually the 4 years, a little more than 3 years existence of CMBR, we took advantage of our participation in MBRC, so it was for us very good that we were able to use their experience and take lessons from this. Of course, this is a problem that refers to all the matter of how the funding and continuation of the research infrastructures of the Greek roadmap can be continued in the future. is a very serious problem. Of course, it refers to all infrastructures in the Greek roadmap. There are some thoughts on how it could be done. The most likely that is going to be, this is going to be done in the context of the next framework period, which the priorities of which are just now being shaped. So it may take maybe for a couple of years. This is a problem. I know that there are other also, not from official sources, but just in the corridors, that there are also other attempts. For example, in the context of the new foundation for funding basic research, ELIDEC in Greece, that they will try to find ways to cover the gap. But of course, the projects are very close to end, and unfortunately, there will be some problems in having them running flawless. Of course, we try to persuade the political people, the government, that it is not very prudent to spend a lot of million euros, because I think the supporting so far of the Greek research infrastructure has costed approximately 70 million euros. And then to have a period which would jeopardize their existence. I think they understand it. They are trying to find ways. We just have to wait at this point and press.
And do you think that, a question by Nicholas Spade, what can European RIs do to support the sustainability of national nodes?
I think in our case, EMBRC has shown exactly what can be done. I mean that they have supported us in our meetings with a request with the region of Crete in order to have some certain kind of support, but not only to the regional authorities, but also to the national authorities. Of course, they could be of great help, but I'm sure that they will do so. Because I think what it is understandable now in the authorities is that the research infrastructure is a very important factor, and we have to go into this. It would be a big failure if Greece would stay away from the new wave of research infrastructures being developed in Greece. And as I said, is not only the MBRC, this refers to all infrastructures in the roadmap.
Okay, great. Antonis, thank you very much.
You're welcome.
Contribution. And now I was in a hurry previously to invite the talk of Dr. Nikos Papandroulakis. Nikos is research director in aquaculture group of our institute.
Good morning, dear colleagues and participants. Thank you for being with us today in this event. I will present our work towards the design and the construction of a multi-use platform in our area in the Eastern Mediterranean. It is a teamwork with people involved from the Hellenic Centre for Marine Research, the Technical University of Crete, and the Hellenic Mediterranean University. The first question to answer is why a marine platform as research infrastructure? Although there are several answers to this question, the most important is to provide a long-term access to marine ecosystems, particularly in the open sea. This will allow us to study and understand the new environment, to develop innovative technologies, and to support multidisciplinarity and coexistence towards sustainable blue growth. We have a particular interest for the aquaculture and the renewables, as I'll explain later. And of course, we would like to have a reference point for the marine research in the Mediterranean. There is a lot of discussion for the reasons why aquaculture should move offshore, and these include the existing competition in the coastal zone and the improved environment for the rearing that will allow better growth, health and welfare for the fish, and of course the potential for increased production. There are already available systems for production offshore elsewhere in the world. Energy from the sea is again something that is based on the competition for the use of land and of course for the exploitation of the available potential which in the case for wind power is more stable and of higher density. This resulted also here in mature technologies for wind turbines and floating solar panels, and to a lower degree for current and wave energy. In Greece, aquaculture is an already established activity, well expanded all over Greece, all over the country, but not exploiting yet the offshore environment. On the other hand, there is a huge potential for the marine renewables based on already available studies. So we consider that we have an opportunity here for these two cases. In this project, our targets was to provide a conceptual design of a multi-use platform, its power design, definition for a possible location for installation, together with a licensing procedure and some preliminary construction studies. The general characteristics for the platform include the location, the construction, and the anchoring. And we thought that an area something like 10 kilometers from the shore and with depths between 75 and 100 meters is quite representative for our region. For the construction characteristics, we consider an arbitrary geometry and quite variety for different materials, while we thought that a surface of between 500 and 1,500 square meters would be sufficient for the activities that we plan. For the anchoring, floating production systems or tension lengths were considered having flexibility for the design. The lab facilities include one for offshore aquaculture with a cage for pelagic species that will be attached to other elements of the platform, an environmental observatory with system of sensors, analytical labs, and a mesocosm infrastructure, a lab for marine renewables for the production of energy from different sources, aeolic, solar, wave, current, and so on, connected to a smart grid, and a general lab for offshore technologies that will allow the testing of systems for communication and remote observation and control, and also of equipment like ROV and AUV. For each of these labs, we describe the installed infrastructures, being these cages, lidars, sensors, etc., the activities that we expect to have there, the workflow and controls on a daily or periodic basis for inspection and maintenance, and of course the flow of the personnel and the material. All these were essential for the design and the dimensioning of the platform. There are common facilities, of course, on the platform that include the desalination unit, a sewage treatment plant, a central control unit with telecommunication systems, security, accommodation areas, workshops, obviously boats and their docking requirements, and a crane for loading and unloading material. These sum up to a total area of approximately 1,300 square meters. During the design, we consider different standards, and you see here the list. I'm not going to get in detail, but we have them all in mind during the preparation of the study. Coming to the power design of the platform, a hybrid power system was considered based on renewables, mainly aeolic and solar, storage system, and a control production unit that will allow autonomous operation of 2 to 3 days. After modeling the meteorological data and the energy consumption and production, we were able to calculate the needs during the operation and the potential maxima of the consumption. We simulate the operation of the platform with different wind turbines, different solar panels, batteries of different capacity and technology in order to provide the optimum battery generator selection and to simulate different maximum power values, always under a smart grid operation. For the possible location, we explore the knowledge that we had from the European Tropos project, that we were defined areas close to Crete based on different criteria for aquaculture, wind energy and wave energy coexistence. And we came up with locations at the northeast of Heraklion. Based on these initial results, we considered further the area south of a small islet at the northeast of Heraklion, with the characteristics that were appropriate for our study. As you can see here, its distance from the shore and the depth in the area. And we have also some values of the wind velocity that are about 7 meters per second, and at 50 meter high it increased to 8 meters per second. With a side scanner, we had a description of the seabed and its substrate that will allow us to better estimate the requirements for anchoring of a platform in the area. Coming to the licensing procedure, as usual, this resulted in a quite complicated approach that involved, in this case, 3 ministers, the one of the Environment, the Maritime Affairs, and the Ministry of Finance, and of course, the region of Crete. At least now we have a clear procedure to follow when this is going to be required. Based on the above, we came up with an initial design of a triangular platform, either equilateral or isosceles. And here you can see some pictures of its view with a different facility, a top view, and also below the platform, a view below the platform at the sea level where you can see the aquaculture cage. We continue our work with specific studies on the hydrostatic and hydrodynamic analysis, the aeroelastic and aerodynamic analysis for the wind turbine, a combined hydro-aeroelastic analysis, and of course the design of the anchoring system. All this has been outsourced at specialized parties, and their implementation completion is expected by the end of the project. The next step for us is to prepare a technical dossier for the construction and to go to appropriate bodies for certification. A final comment for the reasons that we perform such a study. It is well known that in North Europe there are similar technologies and more are developed. Also in the Mediterranean and particularly in Spain, there are pilot applications, not without the aquaculture yet. And we know that these applications are ready to go at industrial scale, as we shall listen in the afternoon in the presentation. For Greece, we have a huge marine potential to explore, and it is important for us to develop appropriate technologies following a multidisciplinary approach. I would like to thank you for your attention, and I will be ready to answer your questions.
Nikos, thank you very much for the comprehensive presentation of the platform. I have several questions for you. Are there existing open-sea platforms in the Mediterranean or in Europe in general? And in which places? In the Mediterranean, in the Atlantic, North Sea?
It's mostly plant, let's say, multi-use platform. But yet we have only huge marine eolic parks in the north that are planned to be incorporated with aquaculture, mostly seaweeds. For the Mediterranean, as we are going to listen in the afternoon by Pedro Mayorga, there is an initiative to develop floating parks of wind turbines that they want also to match it with aquaculture, but yet there is nothing available. There is no pilot scale activity to this, as far as I know, not only in Europe, but worldwide. And if we succeed to have this platform here, this is going to be unique.
Yes. We cannot hear you very well, Nikos. Thank you.
How's the situation now?
A little bit better.
Okay, should I repeat my answer or was that okay? Of offshore platforms, mostly for wind harvesting, but there is no joint multi-use applications. In the north, they are looking forward seaweed aquaculture, mostly and mussel aquaculture, together with these wind turbines that are located on the bottom of the sea. And there are some floating platforms in pilot scale in Spain that they want also to match it with finfish aquaculture.
And there is a question by Thanos. What is the capacity of the aquaculture farm in the platform? Will it change the scale or is it about the same?
There is no actual design of the cage there. We have some initial thoughts and we have some models that of how we are going to install it, but it's going to be just one cage of that is going to be similar to the size of the platform. There is no final design on this. We expect to have a final design by the end of this year when the project is going to be completed.
And one last question. Okay, there are platforms in the north, but probably the engineering needed there is easier than what you need in the deeper, say, Mediterranean sites. How close or how far we are from the implementation of such platforms?
I've just said before that there are already pilot platforms in the Mediterranean, and they are ready to go industrial in areas similar to the ones that we have. That means in deep areas about 50 to 100 meter depth and away from the coast. I see that there are also questions like the accessibility outside and from companies. It is a general approach for in our project and in our infrastructure that everybody will have access, and there are going to be a committee and a plan for access to the infrastructure in the way that this is going to be implemented. And yes, obviously, if the platform works together with the CMBR and all the facility, we think that this is going to be a hub for the researchers in the Mediterranean, that they can work and use the platform together with us.
Thank you very much, Nikos.
I thank you for your questions.
So we'll now continue with Dr. Paraskevi Pitta, who is researcher in the Institute of Oceanography, and will tell us how we can tame the ocean in terms of experimentation.
Good morning. My name is Vivi Pitta, and today I'll talk about the CretaCosmos facility. I'll try to explain how this experimental tool, in fact, may be used to address complex ecosystem functioning, but also responses to human and natural-driven environmental changes. But first, I'll try to explain what is a mesocosm. Mesocosms are experimental bags or tanks of large volume that allow experimentation at the ecosystem level under controlled conditions. In fact, mesocosms fill in the approach gradient from the strictly controlled laboratory experiments to observational studies of natural ecosystems. And finally, they combine the advantages of laboratory experiments, which you can see here, with the work in the field. In fact, the possibility to address the complexity of natural ecosystems because exactly of the large volume of mesocosms involved. Because of that, we may have members of many trophic levels, so we may simulate the conditions prevailing in the natural environment as much as possible. In these photographs, you can see here land-based facilities or in situ ones in fresh waters. This one is in an estuary or in marine waters, or this is again a lake. Mesocosms have been introduced more than 80 years ago, and ever since they have been used in a large variety of research topics, either to advance our understanding of the food web interactions or the ecosystem functioning, or to address food web's dynamics, resource partitioning, etc., or on the other hand, to study effects of perturbations at the ecosystem level, or study phenomena including climate change. The facility CretaCosmos was created by the Institute of Oceanography in 2009, and ever since it has been member of 3 European and 1 national networks of research infrastructures like MesoAqua, Aquacosm and Aquacosm Plus, these are the European ones, and CMBR, which is the national funded ones. Regarding the facility now, this facility comprises 2 land-based concrete tanks of large volume in which 12 pelagic mesocosms or 9 benthocosms may be incubated. But at the same time, it offers access to a number of analytical labs, also to meeting rooms, a research vessel, a Zodiac, or a mobile lab. What is finally interesting about this facility is that because of its geographical position in the Eastern Mediterranean, which is the lower end of the productivity gradient of the Mediterranean, it allows experimentation in real oligotrophic conditions. In fact, this is the only existing facility that offers this possibility. These are some photographs from the labs I talked about before. And now I try to give you some examples of the use of mesocosms, and I'll start from studies addressing complex ecosystem functioning. The very first experiment we ran in 2009 tried to find an answer to the P limitation of productivity of the Eastern Mediterranean. To do this, we added phosphate in 3 mesocosms, while 3 others were kept as controls. We obtained nice results out of this experiment, which were published later on. The following year, we wished to study the mixotrophic organisms, and to this end, we imposed a gradient of light, as you may see on this photograph, on the mesocosms. In a more recent experiment, we tried to find out about coexistence and competition in the microbial plankton, and to this end, we removed zooplankton, that is the top predator, from 3 mesocosms, and we examined what happens to the food web in the presence or in the absence of this top predator. As opposed to the previous more basic research examples, I'll try now to explain how mesocosms may be used to study the response of the ecosystem to natural or human-driven changes. And I'll start from these two experiments during which we added Saharan dust in the mesocosms in order to simulate the phenomenon, this phenomenon, which is very common in the Mediterranean. These experiments took place in 2012 and 14. A lot of scientists participated in these experiments, and these two experiments produced 14 publications, which were published in a special issue of Frontiers in Marine Science. Another example is the experiment that took place in 2013, during which we studied the simultaneous effect of ocean acidification and warming on the pelagic ecosystem functioning. Again, numerous scientists participated. In this experiment, we kept in one pool, we kept the ambient seawater temperature, which was 25 degrees at that moment. And in the other pool, we increased the temperature by 3 degrees. Here, you see the increased CO2 concentration we had in order to simulate the conditions predicted for 2100. During the burn impact experiment in 2018, we focused on the impact of the in situ burning of oil spills on marine shallow waters. To do this, we burned the crude oil in 3 mesocosms, and with a custom designed and made soot collector, we transferred the soot produced by the fire to another 3 mesocosms. Finally, the effect of low-dose silver nanoparticles on the microbial food web was studied during 2 experiments in 2015 and 2019. Here are some numbers. Up to now, 13 experiments have taken place in our facility since 2009, in which more than 300 scientists participated, and the facility offered 1,250 transnational access person days. All this work resulted up to now to 33 publications, while more than 30 are on the way. In addition, 7 PhD and 3 master theses were produced based on these results. The facility, what is important here, and I would stay a bit here, is that the facility has been used up to now not only by the 4 research infrastructure projects, but also by 7 other research normal projects, 4 of which were European and 3 were national funded, which actually in a part were funded exactly because thanks to the existence of this facility. All these projects in total brought 2 million euros to HCMR. This is a detailed list with all the experiments, with the participants and the publications produced. And these are the research teams of all the experiments and the funding organizations. As you may easily realize, research in mesocosms is a teamwork. And here is the research team that supports the CretaCosmos facility. And with this, I finish. Thank you for your attention.
Thank you very much for this really fantastic presentation. Well, in In genomics, you run an experiment for 1 day and you have data analysis for a year. And here it's not that easy to get data. With this, I take the opportunity to present a question I see here, which is, what are the main challenges that probably we have not seen in your presentation that you face in this kind of research?
Yes, actually the one, I would say that the one really big challenge is at the planning and at the organization aspect, because if you have seen, more than sometimes up to 30 people participate in such experiments. So among which people that are not really familiar to this kind of experimentation method. So we all the time have to be able to guide these people, organize all the activities, and also resolve problems that arise very often, because each time it's a different research topic which is studied. And as you said, these experiments usually take place for 1 week or 2 weeks. Sometimes we have prolonged it to almost 2 months. And the analysis of the results take years after this. And for this reason, it takes time for the publications to appear. And on the big list that I showed before, you can see that I don't know if we may see the, anyway, it doesn't matter. I would say that only the half of these experiments, of the 13 experiments, have been completed regarding publication, because publications come many years after. The other big challenge that I would say, which is very important also, is related to the oligotrophic nature of our environment, and people that come to work in this facility, in most of the cases, do not really understand the extent of this oligotrophism of this environment. When we talk about 2 or 3 nanomolar of phosphate, people are not used to these numbers. And all our methods actually work at their lower capacity, and we have to guide these people with this fact. I would say that these are the 2 major challenges.
Thank you very much, Vivi. This was really a very nice presentation. And now we'll give time, 15 minutes break to anyone to refresh and have a coffee. And we meet at 12:15.
Sorry to interrupt.
Yes?
The conference is running behind, so
okay.
Continue with the next presentation. Is that okay?
Sorry?
I think we should continue with the next presentation because we're running behind.
Okay, then. Okay. I hope you are not very tired, and we keep on going with the next presentation, which is, let us see, it's by Dr. Evangelos Pafilis. Evangelos, you're there?
Yeah, Hugo.
Okay, thank you for this.
Thank you for the introduction.
So Evangelos is one of our 2 bioinformatics researchers. He specializes in biodiversity informatics, and he helped very much in setting up the hypercomputing facility with a great IT team around him. Thank you, Evangelos.
Yorgo, thank you. Thank you all for listening. I would like to apologize from the rest of the presenters. I wasn't able to prepare a video. I would like to go through the talk. I'll be looking at any questions in an interactive fashion, so feel free to interrupt. I'm very happy that this talk is happening today. It's in a session about facilities, and it's in a session about research infrastructures. This is a great opportunity to speak about zeros and ones, that means bits in modern molecular marine research from a high performance computing perspective. And given we are working in IMBBC and according to the scale of our facility, a regional HPC perspective. In this talk, it's going to be a very brief introduction to the techniques happening in IMBBC, a presentation of the Zorbas, the IMBBC regional HPC system, some research that has been supported over the years, and to close the presentation by describing you some lessons learned with this experience and discuss challenges, next actions, and the way forward, something that is in the crossroad of research infrastructure, of connected infrastructures, something that has been mentioned already so many times. Let's see. The content of this talk is currently has been submitted as a review on bits in marine molecular research, and we are expecting the evaluation. In case you are the reviewer, feel free to ask questions. It might help the review go into the creative phase. In addition, following modern scientific practices, the supporting material of the review is available as a preprint in Zenodo. So you can visit this link and find information and statistics about the IMBBC HPC facility history, configuration, usage, and side actions. Next generation sequencing has been a key changer in the field. We got MISEC and MinION in the institute, and there's a lot of sequencing being outsourced, so happening elsewhere. This has helped a lot in projects like genome sequencing, in studying organisms like fungi or microorganisms and environmental DNA samples. This is just an advert for a talk that will follow in the day. Georgios, I'm sure you will speak more about it, on how research happens across the different omics levels, so across the different levels of biological organization and for different clades of the tree of life. Important, besides NGS research, a great thing with IMBBC is that it also involves research like capturing environmental parameters and doing a lot of ecological studies, or doing also biodiversity studies. Here you see colleagues Giorgio Hadjigeorgiou and Eva Hadjinicolaou sampling in the Avratyuko lagoons. I'm saying this because I mean the IMBBC computational HPC facility has to serve projects like have to do with NGS, like read preprocessing, de novo assembly, gene annotation, but also has to keep an eye on other type of analysis as well, like biodiversity index calculation or ecological data analysis. This sounds a little bit more like a cliche now, but sequencing has outperformed the Moore's law. So there's a great thing happening. It's a lot of data coming. And how do you manage this data? How do you handle? How do you compute? Many cases, you have to go beyond the capacity of an everyday workstation, like a desktop or a laptop. And that means you have to go into specialized systems. When you go into specialized systems like servers, you have to learn new terminologies. You have to use the command line. Sometimes you have to find your way around. So there is a problem of how to avoid the Babel Tower and to establish a communication across the different terminologies and scientific fields. This is a classification scheme of high-performance computing systems. We are here, we are below the 50 teraflops, and we are a regional system. And you can find more about the information about the facility at hpc.hcmr.gr. This is not now. I've been involved, practically highly involved since 2017, 2018 and onwards. This facility is more than a decade long. And I have to say, it's connected with capacity building projects like Marbigen, RegPod, so Regional Potential Project, the LifeWatch Research Infrastructure, and now the CMBR Research Infrastructure. And I'm very thankful to PIs like Antonis, Dr. Magoulas, or to Christos, Dr. Alvanitidis, now the LifeWatch Eric CEO, that were supporting the facility since the beginning. So Zorba is the HPC from 2015 and onwards, and is a system of 8.3 teraflops strong. Some may call it a strong server, not an HPC. Let's see what a system can produce. So it comprised 20 nodes, a few hundreds of cores, 2.3 terabytes of total RAM, and very important for marine research, it has high memory nodes. High memory nodes, which are essential for working with non-model organisms, like to do de novo assembly or global scale biodiversity index calculation. And I'm quite happy to say that thanks to CMBR, a 1.5 terabyte node is being prepared as we speak. Software-wise, Zorbas involves more than 200 libraries of bioinformatics software, either NGS or biodiversity or ecology. And there's a lot of R, Python, and Perl in there. By the means of easy maintenance and user guidance, it is now being organized as environmental modules. These are some statistics. We have in total a bit less than 100 users with around 20 active users. I will come back to this slide later in the talk. Just a number. In the 2-year period from January 2019 to January 2021, there have been around 44,000 jobs. Since 2017, more than 20 research projects have been supported, and the support included the local researchers, but also the collaborators in other European research institutes. You can find more about the different studies that have been conducted in the HPC, the computational part, by visiting hpc.cmr.gr use-cases. There in the website, you will find the publications listing as well. I apologize, it's not the most up-to-date one, but here you see the 47 publications we've collected that have been supported since the beginning of the IMBBC HPC facility a decade ago. There has been a thorough study, and I have to thank colleagues Haris Zafiropoulos and Natasha Yotti for the intense effort in categorizing them into different types of research, like eDNA-based community analysis or phylogenetic analysis, and finding out when things go from green to red. So when things get tricky, like which type of analysis needed more than 128 gigabytes of RAM, or they needed a lot of storage. If you want to find out more, I hope the review goes well and you can hear about some of the points made. Also, you can look at the supplementary material preprint. I'll be quick here. Some of the experience gained over this decade. Bioinformatics HPCs, you see here that out of 44,000 jobs, only a very small number, look, the scale is logarithmic, so take a note of that. Only a small number needed like more than 64 gigabytes of RAM, and even less needed more than 128. However, they are extremely crucial. I mean, you can't get an assembly completed, you can't get your publication, you can't get your research completed. So in the field, there is a need for a lot of nodes with low or medium capabilities, like slim nodes, but you also need a few very strong nodes in this case with memory, you also need fat nodes. So we've got a depth and breadth requirements. Storage is always an issue. We are trying to address this by installing more hardware and also training the users on how to keep their home folders tidy. And we have been working on parallel bioinformatics software, which is not optimal, but there are things one can do. Very important, and coming back to the Babel Tower issue, intercommunication. You have to get the analysis conducted. You have IT experts speaking to biologists, speaking to ecologists, speaking to bioinformaticians. And to do this, we've been running lots of meetings with users of the facility. In the pre-COVID era, it was like 10 meetings per year. Complementing that is a thorough documentation on how to get started and work with the HPC system, and things like policies that set the requirements to access the cluster, or they provide you with a different level of resources depending on the project that you run, if you are a simple or an advanced user. And more is needed. You need things like booking systems, or you need ticketing systems, so you can ask for a library to be installed or to declare when an analysis is coming. And that would not be enough. There is a lot of training. This slide covers a decade. And it's great that IMBBC has been supporting this. A range of courses that took place at the Institute or in collaboration with the Institute, promoting HPC use and HPC supported research. Last but not least, the way forward, develop locally and share centrally. Locally, as Professor Savakis pointed in a meeting, is not a geographical term. It's a functional term. It refers to the advantage. I think also, Nicholas, you mentioned it in your talk in the beginning, being close to the researchers, the advantage of working locally. This means that you can support your research, but also share that expertise to the others. First of all, CMBR is planning the upgrade. We talked about the extra high RAM nodes coming up, but also the storage to alleviate some of the storage issues running in our facility. However, challenges still remain. Like, you will need more storage. How do you back up your data? What about sustainability? It is true that centralized resources, they can buy, for example, the same hard drives at a much better price from the same providers, just because they buy in bulk, they buy at scale. So how do you go about? You go about with collaboration. Here is a first example. This is the CPU usage in the IMBBC HPC cluster in the 2-year logging period, January 2019 to January 2021. And you will see that most of the time, 50% of the capacity was available for others to reuse. So this is one option when there are not peak usage times. Interconnected resources could offer this to other institutes, following certain agreements, of course. Here is another example. We spoke about the facility and the research happening here for more than a decade. This means that there's a lot of legacy software, a lot of experience in there. And it is now that modern technologies like containerization allow the packaging of selected software and sharing it to other computational systems. Some examples, we go PIMA for metabase coding. There's software running stacks and supporting large sequencing and HPC environments. There is a container with ecological functions taken out of live, which is RVLab, and there is also a text mining container. What you can do is that you can package your application, so you convert your experience in something that you can easily share and run it in other infrastructures. There is collaboration with LiveWatch Eric, like Pima and the RV Lab are being introduced into the Tesseract engine, workflow engine. Follow up the LiveWatch news. There is an interesting workshop happening next week, if not mistaken. We are also collaborating with Elixir. We are collaborating with the Elixir Greece centralized infrastructure that will be called Ipatia. And we are offering access to the users of that community. There is also collaboration with other infrastructures like bioimaging and clearly EMBRC. The team. I'm very thankful to Dimitris, Antonis, and Stelios for taking care of everything from hard disks and technical stuff to low-level system administration to installing the latest bioinformatics library available. And a lot of people have contributed to this talk, either with slides or with figures. I'm grateful to them. I will come back to the preprint where you can find more information if you want, and mention that this is a multi-person, multi-people effort over a decade. And I'm also thankful to colleagues, for example, in the Elixir Greece Resource Allocation Committee for sharing novel ideas on how to move forward. Haris and Natasha for doing the thorough study of the publications, and you for listening.
Okay, Evangelos, thank you so much for presenting one more infrastructure that CMBR can be proud about. We'll not take any questions. You can ask questions in the chat, and Antonis and Evangelos can answer it. I have one that Evangelos, if you can answer it in the chat shortly. And this is that the digital era is really not it's not an easy transition to the digital era. Maybe new programs in the universities are required and so many things, and we see the difficulty. Do you think that RIs can contribute in facilitating this transition? Just if you can answer it in the chat, I will be grateful. And thank you for your presentation. And now we'll pass to the next talk by Dr. Thanos Dalianis, which is a researcher and an expert in marine biodiversity.
Hi, I am Thanos Dalianis from the Hellenic Centre for Marine Research, and my presentation will be about the underwater biotechnological park of Crete, a multi-use experimental platform that is unique in the Eastern Mediterranean and supports the development and demonstration of research projects related to blue growth. Understanding the interactions between the physical, biological, chemical, and geological marine systems is currently a challenge for marine research, especially under the light of climate change. The establishment of a global network of coastal observatories provides the means to accomplish this goal and is at the core of several EU infrastructure projects. In this framework, the Underwater Biotechnological Park of Crete, UBPC in short, is an applied research infrastructure located in the Eastern Mediterranean. The stated aim of the facility is to support the development of pilot research, demonstration, and technology transfer on marine biological resources, aquatic conservation, and sustainable ecotourism. The idea for an underwater experimental and demonstration facility was conceived 20 years ago in what was then the Institute of Marine Biology of Crete. However, since the concept of a seafloor research facility was a pioneering one with no prior example, this was just the beginning of a long licensing journey. After an initial approval of environmental requirements in 2001, the underwater area was initially bestowed for use in 2007 by the Greek public administration. An additional licensing followed in 2014, acknowledging UPPC's compliance with updated environmental legislation, and only since 2015 the facility operates under its current name and form. The park comprises a seafloor area of 2.5 hectares at an average depth of 20 meters. It is located 1 nautical mile north from the research facilities of the Hellenic Centre for Marine Research in Crete. The area occupied by the park is 200 meters long and about 100 meters wide. Its seafloor consists of coarse sand with occasional small reefs, seagrass meadows, and macroalgae. On the left, a bathymetric map of the seafloor at the broader park area shows the sea bottom morphology, which is dominated by escarpment of fault Posidonia meadows, creating a leveled structure. UPPC supports applied multidisciplinary underwater research and technology demonstration and has the capacity to simultaneously host several research projects. Its main objectives are the continuous monitoring of coastal environmental parameters, the accommodation of biotic monitoring schemes, the experimental cultivation and study of marine biological resources, as well as the development and testing of methods in fisheries management and marine ecotourism. Underwater operations at UPPC are carried out by the Scientific Diving Unit of HCMR. Visits for the deployment of experiments, maintenance, and development actions are facilitated by a dedicated small boat. Construction works and deployment of heavier infrastructure are performed by larger oceanographic vessels operated by HCMR. At the core of the park lies the Seafloor Observatory, an array of 3 autonomous oceanographic instruments continuously monitoring environmental parameters. The instruments include a CDD, recording temperature, conductivity, and dissolved oxygen, a fluorometer, recording turbidity and phytopigments, as well as an acoustic Doppler profiler, recording water velocity over the water column. The Seafloor Observatory is complemented by an array of hobo temperature loggers placed at different depths. Now here I usually present some example environmental data from the observatory, but I will not get into detail here, since I would instead like to focus on the research and demonstration activities hosted at the Biotechnological Park. Now regarding the latter, a main research project implemented at UPPC regards the study of innovative artificial reefs designed by HCMR. The specific reefs are constructed from concrete and are characterized by high irregularity and structural complexity, offering crevices and overhangs of different shapes and sizes. A set of 12 artificial reefs belonging to 3 distinct structural types are currently deployed and monitored at the park. The research concept is to evaluate the suitability to increase biodiversity and their subsequent use in designated areas for the attraction of recreational divers. 2 years after initial deployment, the reefs had already attracted and accommodated a variety of reef-associated fishes, such as serranids and moray eels. Furthermore, they consistently attracted visits by several pelagic fish, such as the greater amberjack, Seriola dumerili. Apart from fish, a settlement of rich benthic communities was observed on the substrate offered by the reefs. The main groups were bryozoans, polychaetes, and tunicates. Several studies performed so far for the census of the assemblages developed on the artificial reefs show a high percentage of biotic cover developed over 3 years following the initial deployment. The dominant macroalgal groups on the reefs are brown and red algae, while the dominant animal groups are bryozoans, polychaetes, crustaceans, and tunicates. Now, another ongoing project implemented at the HCMR Park is the experimental cultivation of sponges. The first sponge species to be cultivated at UBPC was Spongia officinalis, the native Mediterranean bath sponge. This is a valuable natural resource which has been threatened during the past decades due to unregulated harvesting combined with disease incidents. For this experimental work, specimens of 3 distinct wild Cretan populations of Spongia officinalis have been transported live to the park, where they were fragmented into explants and monitored for growth and mortality. Monitoring of growth extending over more than 3 years has shown great potential for the regeneration and growth of the sponge explants, reaching a body volume gain of several cubic centimeters per month. The operation of the seafloor observatory at the park allows the linking of rearing performance to environmental fluctuations. For example, the highest growth values were observed during the second part of the warm season. Based on the expertise gained by the pioneering experimental cultivation of Spongia officinalis, 8 additional sponge species with biotechnological potential are being cultivated at the park for the past year in the framework of CMBR. These sponges are cultivated in new aquaculture arrays specifically designed for the purpose and are monitored to evaluate rearing response. This rearing response will be coupled with environmental fluctuations as recorded by the Seafloor Observatory of UBPC. A third research project currently implemented at the park regards the deployment of arms in order to monitor the status and changes of hard substrate communities in coastal environments and track the migration of non-indigenous species. The acronym ARMS stands for Autonomous Reef Monitoring Structures. They are standardized devices developed by the Smithsonian in the US. In our case, the ARMS are deployed at the park in the framework of Assemble Plus, a multi-partner European project. ARMS are currently deployed by other partners in different locations in Europe and analyzed under a common protocol. The selection of UBPC in this case is important because of the continuous monitoring of environmental parameters and the particular location of the park in the open sea. Apart from the native research projects implemented at the experimental park, several hosted projects have taken place during the past years. I present here examples for monitoring of Posidonia seagrass, testing of novel fish aggregating devices, as well as a long-term experiment on passive acoustic monitoring of fish to assess the biodiversity of vocal fish communities. Moreover, UBPC participates to the Ocean Sampling Day, an initiative that collects samples of seawater from different globally distributed locations at the same time of the year and assesses their physicochemical traits and biodiversity composition. Now, a couple of research projects are scheduled to be implemented at UBPC in the forthcoming months, including the construction and monitoring of an artificial cave that will allow the assessment of Cyaphilus assemblages in dim light and dark conditions. The research objectives of the artificial cave include the monitoring of settlement and succession of sessile and motile organisms, the monitoring of environmental fluctuation and processes inside the cave, such as hydrodynamism and sediment deposition, as well as the experimental cultivation of Cyaphilus organisms in the open sea. One important future plan for UBPC includes the connection of the observatory to the land-based facilities with the construction of an underwater cable. This infrastructure will allow the real-time data transfer as well as the uninterrupted powering of the instruments. Moreover, deployment of cameras is scheduled that will allow the recording of real-time transfer of video from the park. This is expected to be particularly useful for monitoring and education. Among the future plans for UBPC, education plays a major role. The park is in close vicinity to Crete Aquarium, a public aquarium operated by HCMR and attracting thousands of visitors each year. The possibility of live picture and real-time data from the open sea setting of UPBC could help familiarize the audience with the methods and priorities of marine research. Furthermore, the park is ideal to host scientific diving courses as well as citizen science projects. Currently, HCMR operated 2 such projects, both focusing on the study of marine biodiversity. Last but not least, the Underwater Biotechnological Park welcomes collaboration with researchers for the implementation of original research concepts. By providing access to a range of typical Eastern Mediterranean ecosystems and being highly accessible and consistently monitored, UPBC is an important testbed for the investigation and demonstration of concepts and technologies aiming to promote blue growth in the area. Many thanks for your attention.
Thank you very much, Thanos, for having prepared this very nice presentation, which shows how the sea looks like under the blue surface. It comes to my mind directly the question, the facility is called Underwater Biotechnological Park. And we have noticed during your presentation that we can address ecological succession, that you have it for years in land, but it's not that easy. How do you feel to combine, say, biotechnological and ecological approaches in the same facility? It sounds like strange, isn't it?
Thank you, Yorgo, for this question. I think nowadays ecology and biotechnology are tightly combined. It is interesting that the initial name of UPBC was the Ecotechnological Park of Crete, and then the name was changed later to Biotechnological. As we have found, the possibility to monitor these organisms in the long term provides important clues for their potential biotechnological applications. This regards either the cultivated organisms, like the sponges. Now we have also some bivalves with biotechnological interest, and also extends to the succession, as you nicely mentioned, of natural assemblages, which is also very important if you have the opportunity to assess in the long term.
Okay, thank you very much, Thanos. Now you'll see a presentation that I prepared earlier for you, and this will be about the omics facility of CMBR. Indeed, I will only present the genomics part. The metabolomics will be extensively presented by Professor Roussis tomorrow. Good morning and welcome to the CMBR conference on blue growth. Today I will mostly present you the genomics facility of the multiomics platform of CMBR. CMBR is a distributed multiomic platforms with genomics run at IMBBC HCMR in Crete, proteomics in 4th Research Center in Crete, while metabolomics runs in the School of Pharmacy in Athens by the team of Professor Roussis and Professor Ioannou. So, CMBR offers a multiomics platform for systems biology, which allows to unlock the processes leading from genomes to phenotypes and products, and from genomes to ecosystems, and allow the study of ecosystem functioning. So the genomics which I will talk to you today, and its relation to marine biodiversity, genomics is a set of technologies and methods allowing to decode and study the complete genomes and transcriptomes of organisms or communities in their environmental and phenotypic context. It is achieved by next-generation sequencing technologies, producing big data which require hypercomputing facilities for the management and analysis. It came out that next-generation sequencing evolved in the fastest and most effective way to decipher marine biodiversity. It allows to identify organisms, where they are, when and in what numbers, what is their function, what is their origin, their adaptive value, of the genetic variation. The two technologies used in the CMBR is the Illumina technology with a small Illumina MiSeq and the miniaturized technology of Oxford Nanopore, which allowed long reads and is ideal for whole genome sequencing. Here you can see the evolution over time since the beginning of the Oxford Nanopore technology, which shows that this is a very fast evolving technology. Week after week, we receive new protocols, and Dr. Jon Ben Christoffersen, he is really at the cutting edge of the application of this technology. And here is a graph showing the intensive investment of CMBR in Oxford Nanopore, which allows high quality whole genome sequencing in small labs. So you can even get data in the field with this technology. And so I will present you some examples of projects that have been hosted in CMBR with projects in aquaculture, biodiversity, biotechnology, or organismal biology, and which have been also served by the hypercomputing facility Zorba. Of the application of the technology DDRAD, which allowed to identify 1,600 single nucleotide polymorphisms. These data have been applied of samples collected from all around the globe and have demonstrated that there are basically two genetic stocks, the Indo-Pacific here and the Mediterranean, while the Atlantic populations seem to be of mixed genetic origin between the two others. In addition, it allowed to identify here individuals in the Northeast Atlantic and in the Central Atlantic that are of Mediterranean origin, showing that this population, the Mediterranean, which reproduce in Eastern Mediterranean, undertakes migratory moves in the feeding grounds. These data are really valuable for fisheries management, and by monitoring over time these populations by this approach will allow to unravel eventual changes in migratory behavior as a response to oceanic and climate change. And here is a very interesting project where the biodiversity of the hard sediments across European coasts is assessed by using this autonomous reef monitoring structure, this device that sits on the bottom of the sea for some months, and organisms go sit on it. And then by combining with DNA metabarcoding, we can reveal the structure of each site, of each station, and this allowed to reveal very high diversity of eukaryotes in two stations that have been analyzed in Crete and in Sweden, and also to unravel a very big number of invasive species, like 35 species in Crete and an equivalent number in Sweden that would pass undetected until then by any other method. Low coverage whole genome sequencing is a very good method for deep analysis of genetic structure of populations, and this was the case for the analysis of seagrass Allophila stipulacea, which is an invasive species in the Mediterranean. This study allows to confirm that the Eastern Mediterranean populations originate from the Red Sea. And here is a very nice project that have produced high-quality whole genome sequencing of the invasive puffer sea fish in Eastern Mediterranean, Lagocephalus celeratus, by combining Illumina sequencing with Oxford Nanopore sequencing. And this has been made possible thanks to a pipeline of mixed assembly that have been developed by Dr. Manusaki within CMBR. Then by combining whole genome sequencing of sea bream with DDRAD data that you can see here in this paper, Dr. Tsigenopoulos obtained thousands of SNPs, which analyzed together with interesting phenotypes for aquaculture, allowed the identification of the genetic basis of phenotypic diversity, and now these data are applied in selective breeding projects in the aquaculture industry. Well, their developmental stage in fish is a very complex story because of the history of evolution of these animals, and Elena Saropoulou used RNA sequencing either on mRNA or non-coding RNAs to study these processes, together with the evolution of the mechanism of early development and the evolution of gene families of fish. CMBR is very much interesting and supported by prospecting projects to explore the hidden biodiversity of the marine environment. So it works on microalgae, on bacterial communities, on marine fungi, and on sponges to this end. Multiomics research in diatoms allow to study the local diversity by isolation, culturing, genomic and metabolic characterization, while Dr. Frédéric Verret at the same time applies reverse genetic approaches to study RNA interference mechanisms, and also applied research by unraveling the biosynthetic pathway of the blue pigment marinin, which is of high importance for aquaculture. This is a very interesting project when Pseudomonas strains, bacterial strains, have been isolated from waters over the Colombo, the underwater submarine volcano Colombo, and have shown that the strains that live in CO2-rich waters close to the volcano surface have phenotypes and gene clusters that allow them to have strong antimicrobial and multi-drug resistance. And metagenomics data on other communities of the Santorini volcanic complex allow to detect gene clusters specifying enzymes interesting for bioenergy. This research continues now on applied projects by Dr. Polymenakis. And here is a project hosted, a project of the Technical University of Athens of the team of Professor Topakas, which investigates PCB remediation and multi-copper oxidase activities. Here working on isolates from all around the globe, he identified multi-copper oxidase activity in one of the strains. Then the enzymes have been isolated, and targeted proteomics combined with bioinformatic analysis of the genome allowed to identify the pathway leading to PCB remediation. And this research continues and is very promising in terms of applied research. Finally, CMBR works on sponge genomics and is interesting in general in symbiotic organisms. Sponges are symbiotic organisms by excellence, made up of the animal sponge, microbial communities, which make up the most of the biomass of a sponge, like photosynthetic organisms or fungi. We started working on the sponge by transcriptome analysis, and now we're continuing with whole genome sequencing on the collections of different sponge species from Eastern Mediterranean. Thank you for attending, and thank all CMBR users. Well, dear all, thank you for having attended this morning session. And If you have any questions for me, please write it in the chat and I will answer it written. And now we have almost 30 minutes break until the next session, which is the Blue Growth Concept, Policy Management and Economics. Please stay tuned with us.